Hello everyone, my name is John Salma. I'm an assistant professor at St. Joseph University of Beirut. I'm going to present here this paper entitled Dynamic Stabilization-Based Trajectory Planning for Drones. This work was performed by Dr. Ana Ajami, by myself, John Salma, and by Dr. Jeffrey Malik. First of all, unmanned aerial vehicle or UAVs are used in many applications, such as surveillance, control missions, monitoring, delivery, and fixed and moving target tracking. In this paper, we are going to focus on fixed-wing UAV. These drones should not travel at very low speed. Usually, these drones have a minimum speed. If they fall below this speed, they risk to stall. We are going to develop for this type of drones two tracking control algorithm for tracking a fixed and a moving point. The first one is a basic tangent method, and the second one is a stable Lyapunov-LaSalle based method. This presentation is organized as follows. First of all, we will start by modeling the system. I will present the basic tangent method, then the Lyapunov-LaSalle tracking method. Then I will present simulation results, and finally I will conclude and present my future work. Let's start by modeling the system. Since we are using fixed-wing UAVs, we will consider that our speed or the speed of the UAV is constant equal to 1, and we will consider that the UAV is traveling at a constant height. The kinetic model of the system is presented here in 1. The input of this system is denoted by U, and this input is the rotating speed of the UAV. So our input is that we are capable of rotating the UAV to the left or the right. And our objective is to track a specific position or specific target on a specific position. Here the position is denoted by X and Y. Let's start by the basic tangent method. As we can see, our fixed-wing UAV is always traveling at a constant speed. That's why we are not able to intercept and stop our UAV at the target. We should hover our target, and we are going to use a circular pattern to hover this target. We'll also assume that our target is located at X equals 0 and Y equals 0, and the UAV is located at or has an initial position of X, Y, and Psi. This first algorithm is an open loop tracking control algorithm, or in other words, it's a pre-calculated tracking algorithm. What we are going to do is that we are going to calculate the input that we are going to give to the UAV in order to track our reference. This first method is summarized by the following steps. First of all, we will compute the tangent to the hovering pattern. As we can see here in this figure, we have two tangents to the circle, the hovering pattern. We will choose the nearest one. So what we are going to do is we are going to rotate towards this tangent, slide onto the tangent till we reach our hovering pattern, the circle, then we are going to slide onto this circle. Now let's switch to the second control method. The second one is a closed loop control method. It is based on using the Lyapunov-LaSalle method. It is a stable method, but to create or to compute this method, we are going to use the following steps. First of all, our stable point is a circle here. So we are going to switch from our stationary frame to a new frame where the circle or the stability is a point. That's why we are going to apply a first transformation here presented in equation 3, where going to switch to a rotating frame. Then we are going to apply a translation presented here in 4. By applying those two transformations, our stability will become a point, and the equation of the UAV in the new rotating reference frame is presented here in equation 2. Now let's choose a Lyapunov function in order to derive our controller. The Lyapunov function is presented here in 5. It's a x bar squared plus y bar squared, where x bar and y bar are the coordinate of the system in the new reference frame. After doing that, we are going to compute the derivative of the Lyapunov function, and we can find here that input 7 could satisfy 5 and 6, and v will become a Lyapunov function by applying 7. It is not enough to apply 7. We have to choose 7 in a way that not only we guarantee the stability of the system, but we also should reach our hovering pattern using the tangent. That's why we are going to choose a specific function k, which is inside equation 7, in order to achieve this. The chosen u is presented here in 8, and now I am going to prove why 8 could achieve our objective, which is hovering in a stable way the target using the tangent. We'll choose here a new Lyapunov function. The new Lyapunov function is presented here in 10, and this Lyapunov function is v1 equal y bar squared. The derivative of this Lyapunov function is presented in 11. As we can see, if we can prove that v1 is a Lyapunov function, this means that y bar will converge towards 0. And if you can prove that y bar is converging towards 0, that means the UAV is sliding onto the hovering pattern using the axis x bar, and the x x bar is the tangent to the circular pattern. So in case v1 is a Lyapunov function, that means this controller could slide to the hovering pattern using the tangent to the circle. I'm not going to do the whole demonstration. The demonstration is presented in the paper. But yes, actually v1 is a Lyapunov function, and the proposed input to the system could ensure stability, and at the same time will ensure that the system will slide using the tangent to the hovering pattern. This algorithm is summarized by doing the following step. First of all, measure the AV position. Then we will switch to the new rotating reference frame. After doing that, we'll compute U, equation 8, which is the control law. And finally, we will apply this input to the system. Here I am presenting the simulation results of the two methods, the basic and the Lyapunov-Lassalle method. Both of them are doing their jobs, but of course, the basic tangent method is a open loop method. So maybe in real life, if we are capable of doing experimentally this method, we will see that most probably this method won't have very good results as the one presented in simulation. And here we are presenting the simulation result when we are tracking a moving target. Also, both of these methods are doing their job. Finally, this paper presented two methods, the basic method and a stable Lyapunov-Lassalle method. Both methods are giving good results. As a future work, we will try to test this method experimentally in real life and show their performance. Thank you for listening. Your questions, please.